Good day, class. In this lesson, we will study solving logarithmic equations. Notice in our first example, we should be able to read our expression log base 5 of x equals 4. Also recall that it's important to rewrite your logarithmic equation in exponential form when you have a single log term. I have a single log term here, so I'm going to rewrite that. 5 raised to the 4th power is x. Now I'm going to just play that out. X is 625. I'll probably substitute that back into my original equation to make sure it makes a true statement. In my next example, log base 2 of x equals -3. Nothing really changes here. I'm going to rewrite this in exponential form. 2 raised to the -3 equals x, and then I can play that out. Remember that the rules for dealing with negative powers, you can either move that power to the numerator or denominator, and that will help eliminate the negative. Here I really have 1 over 2 to the 3rd power equals x, and then that 2 to the 3rd power is going to give me that 8. So 1/8 is x, and I can apply that back to my original equation and discover that my unknown, the value of my unknown is 1/8. Here, I'm dealing with the natural log, so my understood base is e. So if I want to rewrite my equation, I'm really going to rewrite this equation to read e raised to the -2 is x. And so also recognize that e is an irrational number, but it is a constant value. So I'll just probably deal with that negative power and just go ahead and drop that e squared to the denominator. And now I can see that 1 over e to the 2nd power is my value of x. Maybe I'll apply that back to my original equation to answer my question. Natural log of 1 over e to the 2nd power is -2. In this example, I'm given log base 64 of 1/4 is x. No problem here. I have one single log term on the left. I'm going to rewrite this equation to call this 64 raised to the x power equals 1/4. At this point, I recognize that my unknown is in the superscript. So I'm going to apply the laws of logarithms. I know I'm reaching back to many prior lessons here, but in applying the laws of logarithms will help me deal with that superscript, which is unknown, because according to the laws of logarithms, I can get that superscript down. I can get that unknown out of the superscript by applying the laws of logarithms. So I'm going to take the log of both sides of my equation. That's all I've done in this line. And then I'm going to apply that law of logarithms. And I'm going to go ahead and pull that down. I have x times the log of 64 equals log of 1/4. Each time in each line, I'm just rewriting my equation, whichever expressions need a rewrite, to make it more convenient. I'm going to write it in a way that is more convenient, but I never break any laws here. I never break any rules, and I apply principles along the way that could be helpful. And now I recognize that the log 64 is a constant value. So I'm going to divide both sides of my equation by log of 64, which leaves me with just plain old x on the left and leaves me with log of 1/4 divided by log of 64 on the right. At this point, you just sort of are getting used to dividing by values that aren't constant, that don't appear to be constant, like we have in the past. So that log base 64, that log of 64 is a constant number. So if I want to isolate my variable x, I can just go ahead and divide both sides by log of 64. At this point, I'll probably use my calculator, pop that in. I could use a log chart, so many things I could do here, but it'll be really easy to use the calculator. I encourage you to embrace it so we can really spend our time absorbing the many other ideas that we will encounter in this course. So hopefully you will consider using your calculator here. X equals -1/3. I'll put that back in my original equation and expect to get a true statement. Here I'm given log base 2 of quantity 10 plus 3x equals 5. I won't change my mind. I have a single log term on the left. I'm going to rewrite it in exponential form. So what I really have is 2 raised to the 5th power equals 10 plus 3x. From there, it becomes really simplistic because we're actually looking at a linear equation. We'll go ahead and isolate that variable x based on your prior knowledge, and then we discover that for the original equation, probably the value of x is 22/3. We'll substitute that back into the original equation and make sure that gives us a true statement. In this next example, we have noticed two log terms on the left-hand side of our equal sign. Now, remember, I'm accustomed to having that variable on the left, but the variable could very well appear on the right. Even so, I have log x plus log quantity x minus 9 equals 1. I have two log terms here, so I need to combine those so I can have that single log term, and then that'll give me the privilege to rewrite in exponential form. However, I can't just distribute that log. It kind of feels like it because we've been distributing for years throughout a parentheses. But this is log base 10 of quantity x minus 9. So we can't ignore that 10 there. So what we really want to do is apply the principles of logarithms, those laws that apply to addition of logarithms. Really what we have here is the log of x times quantity x minus 9. So these are the same. This equation is the same, the first line and the second line, just one is written in a different form, a more convenient form here. So, and then we'll apply the principles. We will refer to the principles of logarithms to recognize that when we're adding those terms, we can really combine those values, that x and that x minus 9, via multiplication. Now I have a single log term. I can go ahead and rewrite this I'll distribute that first, but then I can go ahead and rewrite this log equation in exponential form. So what I really have here is 10 raised to the first power equals x squared minus 9x, and I just got that x squared minus 9x by multiplying that x through the parentheses. Now I have a pretty simple quadratic equation. I can just look for the most appropriate way to deal with my quadratic. Here I find that factoring works just as well as some other methods, so it's quick, it's easy. I'll isolate my variable by using this property, zero product property. And so I have x plus 1 equals 0 and x minus 10 equals 0. And then I discover that x equals -1 is a possible solution, and also 10 is a possible solution. However, if I substitute the original, these solutions, possible solutions, back into the original equation, I will find that this x equals -1 happens to be an extraneous solution. Now, negative solutions are not always extraneous or always extra, or always discardable, but this one happens to be, because if we try to take the log of -1, it won't make sense. And so I will refer you, and for the sake of time, also to prior lessons which describe the reason that that doesn't make sense. So we'll just go with that single solution of x equals 10. And in our final example, we're given log base 2 of this quantity x plus 20 minus log base 2 of this quantity x plus 2, and that's all equal to log base 2 of x. So in this example, I'm noticing also I have multiple log terms. If I can get a single log term, then I can rewrite in exponential form. So I'll start working on that. Let's apply a principle of logarithms. Here we notice, which is a little different than the previous example, that we are subtracting these log terms. That gives us the prerogative to divide our x plus 20 divided by x plus 2, rewritten. Now I still have two log terms, one on the left, one on the right. I want to combine them. So I'm going to get them together. Now keep in mind, your methods are just as good as my methods as long as we don't break any laws. So you can go in any direction you want, just don't break any laws. Here I'm going to, now that I've gotten my log terms on the same side of the equation, I'm going to apply log terms again. Remember, subtraction is going to suggest the division of those quantities. So now I have x plus 20 divided by x plus 2, all divided by x. And that's going to be equal to the 0 I left on the right-hand side of the equation. Feel free to pause this video if you're a little short there and not quite sure. Even so, now that I have a single log term, I can probably simplify a little bit. So I'll try to work on some of my knowledge of dealing with rational equations. I'm going to put an understood 1 under that x in the very far denominator, so then I can maybe multiply here by the reciprocal, and it sort of simplifies my life a little bit. Once I combine those terms, I'm looking at something a little more simplistic, and now I'm ready at this point to, as soon as I get this completely simplified, as far as I can go, I really can consider rewriting this in exponential form. Now I have written 2 raised to the 0 power equals all the rest of my material there. At this point, I just want to continue to simplify. Any number raised to the 0 power is 1. Also, I think I described that in a previous video, the reason for that. And now we just have kind of a simple quadratic equation that we can just work through. We multiply that denominator across on the left side of the equal sign, and then we just isolate our variable the best way we can. And this way I'm discovering that I do have a quadratic. Maybe I'll try to factor, and it works quite well. Now we're just looking at 2 possible solutions. I'll check those solutions to make sure they both make sense in the original equation. Remember, you may need to refer to a previous example, but even so, in this case, or a previous lesson, forgive me, but in this case, I want to discard my x equals -5. Now, don't mistakenly believe that all negative solutions are extraneous, but in this example, x equals -5 is not permissible. Again, we can refer to a previous lesson to really get a true understanding of why. We only have one solution here that will make a true statement in this equation, and that will be x equals 4.